Okay, we're going to start chapter 7, where it's going to be mostly, pretty much exclusively about bonding. We will look at bonding, we'll make some bonds, create some structures, and talk about shapes, and that'll be the important part of it. So before we start the conversation about the different sections, covalent and ionic, and then covalent bonding, we're going to start with what a bond actually is. So first of all, a bond is an electrostatic interaction which holds two atoms or ions, really nuclei. Whether they're charged or they're uncharged, or they're going to be atoms or not, but it holds nuclei together in close proximity to one another. And that distance is a conversation we're going to have a talk about how close they are, how close in proximity to one another. So bonds are going to be on this scale, and we're going to talk about this later, but I want to create this scale of on one side of the scale, I am going to have ionic. Okay, so an ionic bond is we know this because an ionic bond is a transfer of electrons. And the reason that electrons transfer is because there is a very large electronegativity difference, or delta, right? It's a very large electronegativity difference. And we can identify them by a metal and a non-metal. So whenever you see a metal with a non-metal, generally that's the first indicator that you have a covalent bond. The large electronegativity difference, and I'm actually going to put a number on it. So any delta En, and this number has changed a little bit, but around 1.9, I think your book says 1.7, but there's a reason that I don't love that, and I'll tell you why in a bit. But we see a transfer of an electron. And so how we can imagine this is if I have nucleus 1 and I have nucleus 2, and they each have electrons in between them for whatever reason, or electrons that belong to the two of them. In fact, we can probably talk about it in terms of if this has an electron and this has a bunch of electrons. Okay, so if it has 7 electrons, we know that this is probably in group 7, 1 electron is in group 1. And what we're typically going to see is this electron is going to transfer and fill the octet of that, removing the electron from the other. And now in the end, what you have is you have this positively charged cation and this negatively charged anion, and they are held together because they have this electrostatic interaction. And again, I keep saying this word, and you need to know what it means. Electrostatic interaction is a positive and negative. We know that they are attracted to one another. So whenever you hear electrostatic, that's what we're talking about, positive and negative. So an ionic bond, how we recognize it, metal and a non-metal, large electronegativity difference, which we'll talk about in a little bit. The transfer of electrons is what typically happens. Okay, good. Okay, so if on one side we have a complete transfer of an electron, we have to look on the other where we have a covalent bond. A covalent bond is going to be an even sharing of electrons. So if I have 2 electrons in between, they're going to share it. Okay, this is typically, or in fact always, a non-metal combined with a non-metal, because 2 metals would be a metallic bond, which we kind of gloss over in a lot of ways, but non-metal combined with a non-metal creates that type of bond. Okay, so sharing of electrons, and this is actually pretty easy to, it's still an electrostatic force, and this is kind of the biggest thing. So first of all, let me use the same kind of scale as I had before. So if I have 1 and I have 2, what they do is instead of each having their own electron, what they might do is those 2 electrons would come together and you'd have it in between them. And you're going to form a bond. And a bond contains 2 electrons. So that covalent bond is holding 2 electrons in it. It's important. The other thing that I guess I forgot to mention, I mentioned over there, there is a small or 0 delta En. So there's a very small electronegativity difference. So on the one side, I had greater than 1.9. Over here, the delta En is going to be greater than or equal to or less than or equal to 0.4. So anywhere from 0 to 0.4, we're going to see something, a covalent bond. So let's get a little bit more into a covalent bond. So if I have a positive charge nucleus, there's my nucleus, and I have another, it's still being held together by electrostatic forces, which is positive and negatives. If we look at the ionic interaction, I have a positive, I have a negative. They're held together because one's positive, one's negative. In fact, this perpetuates when you have a bunch of things together, like in a lattice, which we're going to talk about as well. You just continue to make these positive and negatives. It's alternating left and right. This is a really strong bond. The interaction that we're seeing between every single one of these is really strong because it's a full positive and negative. There's no sharing or anything like that. But I said that all bonding is electrostatic, and it's true. So how do we represent electrostatic interaction with these right here? So here's my 2 nuclei, and I said they're electrostatic. So let's see if we can make it electrostatic. I guess I can't zoom in anymore. So here we go. Make it a little larger, I think. So here's my 2 nuclei. Well, if I have an electron in between the 2 of them, or if I have 2 electrons in between the 2 of them, and they're evenly shared, well, we have a couple of things going on. We have to think about the attractive forces that we have. So the interaction between these electrons and the positive nuclei are going to be, those are going to be attractions. So having 2 electrons in between is good. It helps us hold those things together. But of course, we also have to consider the fact that the interaction between these are repulsions. And we're going to see this a lot, especially when we get into intermolecular forces as well. So what we have 2 things. I have the attractive forces here, 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 all 4 of those. And then I have the repulsive forces of these 2. And ultimately the question is, do attractions outweigh repulsions? And if they do, and in fact, we're going to take a lot of looks at this, bonding, anti-bonding, and these other fancy words, but if the attractions outweigh the repulsions, then things going to stick together. So we have created this bond between the 2 of them just by having more attractive forces than repulsive forces. If we move those nuclei together, that's going to increase the strength of those repulsions. But of course, we don't in a normal bond. So there we go. All right. So on one end, I've got ionic. On the other end, I've got covalent. And there's something in between. I drew this for a reason. In the middle, and in fact, I could really call this a large range. So if this was delta En of 0.4 to 0, again, this is going to be covalent. And if this value up here, just to get us on somewhere on the scale, if this up here was a delta En of 1.9, making this ionic and beyond, in the middle, we are going to have something known as, so it's still covalent, but we're going to call this polar covalent. So the delta En is going to have, there's an electronegativity difference. So in the middle, I have polar covalent. It still has the same features as a covalent bond, as in we have an even sharing. It is a sharing of electrons, but instead of sharing, it is an uneven sharing of electrons. And we still have to have a nonmetal and a nonmetal. And that it is a, there is an electrode, there is a delta En. Okay, it's not small or large, it is in between. The delta En is in between those two. So 1.9, less than 1.9 delta En, but greater than 0.4. Those are that's the electronegativity difference. And in fact, that's what we're going to see is if I have, the only difference here is, so before I had an even sharing and those electrons are kind of in between the two, and we can talk about probabilities, and we will when we talk about advanced bonding and whatnot. But now what we really see is, here's my nuclei on one side. I'm just going to make this a little bit bigger, just saying that, oh, maybe that's got a higher, this has a higher electronegativity. The electrons might favor one side slightly. So what you might run into is the electrons might favor being on that side. We still have that covalent bond. It's sharing, but you're going to hear me use this word a lot. But the electrons are kind of, the word is the electron density. The electron density kind of piles up over here. And we'll talk about what this little arrow means. But what you have is essentially, you can imagine this is where the electron density lies. And there's less over here, right? So we would make this a little bit darker because this is where the electron density is. Right, so the electron density is over to the right, although there are still two bonds in between them. It's an uneven sharing of electrons. In fact, I'm not going to bury the lead. I'll just call this thing. This is what we call a polar vector. This is the negative side. This is the positive side. Because right there, there's my positive. Okay. The other way that we would say it is if one side has a charge and the other side doesn't. Slight charge, again, it's not a full charge. Because it's not a full charge, I would say that this side is slightly negative, this side is slightly positive. The small delta means not a full charge, but one side's positive, one side's negative. Okay, so that's bonding, right? That's pretty much what we see for bonding. There's a bunch of different types of bonding that we're interested in. Metallic, we're not going to talk about metallic much, so I encourage you to kind of take a look at them, but it's kind of atoms held together through a sea of electrons. What it really is I guess we'll just look quickly at metallic. Metallic bonds would be, all right, so I've got a bunch of metals and they're all positively charged, a bunch of metal nuclei, and this is typically how I do these, just negatives, then cross them the other way. And then you just have a sea of electrons. So you have electrons in between, because those electrons, those d electrons are kind of free to go wherever they want. Well, all electrons are free to go where they want. But that's why electrons can transfer, because they don't belong to one, so they can kind of travel along. So we have ionic, covalent, and metallic. Those sea of electrons, those nuclei surrounded by a sea of electrons, it's like the glue holding them together. It's also why it's easy to make those malleable. But yeah, so that's the idea behind bonding. Again, it's always an electrostatic charge, ionic to covalent, depending on the difference in electronegativity, which we're going to talk a lot about. So when we talk about ionic bonding, and this looks intense, but I promise you it's not. When we talk about ionic bonding, we form what's called a crystal lattice. Okay, so we have positive and negatives, and I kind of started to show you this up here. In fact, here is my crystal lattice, and I've got it below as well. But what you notice is the positive and negatives kind of line up. So they're arranged with one another. So they're set up, so they're arranged with one another. Yeah, here's my. And we can actually determine how strong that interaction is using the Born-Haber cycle. This is all actually Hess's law stuff. Hess's law, this is called a Hess's law diagram. Remember, Hess's law is the processes. We start with some starting materials, okay, things in their elemental state, and we form a lattice. Again, so this is cesium and fluoride as their elements turned into cesium fluoride as a solid, and we follow it through all of the different steps in order to get to the product. And all that really matters is the overall change in energy. That's all that we really, really care about. Okay. So when we're taking a look at this, what we're really interested in is the strength of that, the strength of the lattice that it's creating. And we're actually gonna have an equation for this. So let me just take a look at quickly how this kind of happens. So we start with elemental compounds, and what we're going to do is we're going to turn them into ions, and then we're going to force them together. All right. So in fact, why don't we just talk about this in class? So we're going to talk about the Hess's law diagram, and I'm going to write this to remind myself. And remind me, please. We'll talk about this in class, because then maybe it'll make a little bit more sense. But ultimately, we have a bunch of processes and we put it back together in that delta H lattice. And so this is what I'm going to focus on now. The delta H lattice is how much energy I get by turning those ions into an ionic compound. And this is the equation for the delta H of lattice. Okay, so K is a constant. Q1 is the charge of the positive charge. Let's say it doesn't matter. You can do plus or minus. And the other one is your Q2. So you could interchange those to one charge and then the second charge. And this is the charge of the ion. So those should be whole numbers, at least in this class. And then the D is the distance between the two. And this is the energy of a lattice. So before we look at this little table, let's confirm what we expect to find on this table. If I increase the charge, okay, what happens to the energy of the lattice? They're directly proportional because they're both on the top. So if I increase the Q, if I increase the charge, I'm going to increase the energy of the lattice. If I increase the distance, okay, so if that number, they're inversely proportional. If I move them further apart, essentially, the distance, I should say, is the radius, the two radii, so the radius of the positive and the radius of the negative. It's the distance that they are apart, the nuclei are apart. So I'm actually gonna just take a quick aside. So the distance is the radius of the positive plus the radius of the negative ion, which you should be able to look up because we know how that goes. So if this is my positive ion and this is my negative ion, the distance in between, that would be the distance. This is the radius of the positive. This is the radius of the negative. Okay, so the bigger they are, the larger that number, the bigger that distance is. So as distance increases, what we see is, again, these are inversely proportional. In fact, it's squared too, so we have to keep that in mind. As distance becomes greater, we see a decrease in energy of the lattice. Which of these is more important? Okay, so look at these. Is charge more important or is energy of the lattice more important? So look at the lattice energies and tell me what you think. Okay. Yeah, and then we'll talk about this in class as well. All right, covalent bonding. So covalent bonding is, we've already kind of looked at this. We've had this discussion about just what a covalent bond is, so I don't really have to get into it too much. Molecules are formed by sharing electrons between atoms formed between nonmetals. when non-metal bond with one another, they share electrons. Since one is non-metal, is incapable of pulling an electron. So basically, because their electronegativities are both non-metal-ish, so they're incapable of pulling things apart, right? So hydrogen is not going to form a positive and a negative ion because they essentially have the same propensity to hold these electrons in. And so what I'm going to look at is we're going to take a look at this little diagram right here. And what I want you to recognize is what we're really going to be doing below, and that's why this is here, is I'm going to have a hydrogen nucleus, and I'm going to start to bring them closer and closer together. And I want to know what happens to the energy when I bring those things closer and closer together. Okay, and that's in fact what we see. So down here, the radius in angstroms, we have two nuclei that are very, very far apart, right? So this is like this point right here, okay? They're really far apart. They're not really interacting, so the energy is essentially zero. But as I start to bring these things closer and closer together, they start to interact. Remember, they have that one electron on the outside. So these things start to interact, and we see the decrease in energy. In fact, as we bring them closer and closer together, again, bring them closer together, we see the energy drop until we get down to this minimum right here. What's going on here? Well, at this point, essentially what we have is, that's probably a bad way to draw it, but we have actually, they're kind of bonded. So I have two hydrogens that are bound together at that point. Okay, so they've got a perfect distance from one another. We have created a bond. By the way, I know the atomic radius of a hydrogen-hydrogen bond is about 1.4, 1.5. So I know this is not hydrogen, it's probably like carbon or something like that. Anyway, we bring those things close together and we have a bond length. Because when we put those things together, what happens if I keep pushing them together? So up here, you notice the energy just climbs, right? So as soon as we get beyond the perfect bond distance, all of a sudden the energy shoots up. Why is that? Well, it's because at this point, the nuclei are like right on top of one another. Now that positive repulsive force is becoming so much that the energy just skyrockets. Okay, so this energy diagram is basically saying, what I want you to take away from it is this. This point right here is the bond length. This right here is the nuclei being too close together. Here is where they're kind of detached from one another. That's all you're seeing from this. You're going to run into this a handful of times, so it's worth knowing that that's what it is. So I talked about covalent versus polar covalent bonds, and I think it's important to kind of take a look at overall electronegativities. So we did look at electronegativities. Let's look at it in a little more detail. So I have electronegativities here, and what we notice is these nonmetals are very large, and then they kind of decrease as we move from left to right. Generally, we don't really care about the metals. We just know that they're generally less than everything else. These are the things that are doing most of the bondings, all of the blue and the purple and the green ones, okay? So let's take a look at three different fluorides. F2, what is the delta? So first of all, let me just get the F, which is 4, and hydrogen, which is 2.1. So we're going to use these below. Actually, I'll get rid of those. So there we go. All right. F2. So I have a delta En equal to 0 because I have a fluorine bound with a fluorine. Both of these are 4.0. And so the difference in electronegativity is 0. That's how we determine a difference in electronegativity. This thing is going to be covalent. Great, delta En equal to 0. By the way, the mu is 0 as well. This is called a dipole, the dipole moment. We're going to talk, we're randomly going to mention dipole moment, but the higher the value, the greater the dipole. Okay, it's something we can actually measure as opposed to electronegativity, which is just kind of fudgy, actually, to be honest. So yeah, let's see here. I'm going to change this color. There we go. Okay, so I have my fluorine here and my fluorine here. On the next one, I have fluorine and I have hydrogen. So the delta En, I have 2.1 here and I have 4.0 here, okay. This is going to be polar covalent with a delta En equal to 1.9. And this is why the extreme, hydrogen and fluorine is generally the extreme. I know it's polar covalent. How? Because it's greater than 0.4 and it's a metal and a non-metal, or it's two non-metals. All right, as soon as you introduce a metal, something changes, and we're going to see that in just a second. So the mu of this is equal to 1.92. The dipole moment is equal to 1.92. Again, we can measure that. We can just look and use the delta En as kind of a scale. Okay, last one, lithium fluoride. Oh, by the way, I would also say that this side, let's do the polar vector. So the electrons are flowing in the direction of the fluorine. And I would actually say that this is partially negative and this is partially positive. All right, let's take a look at the last part here. Let's take a look at lithium fluoride. The delta En in this case, so I have fluoride on one side and I have lithium on the other. Fluoride is 4.0 and lithium is 1.0. So the delta En is equal to 3.0. This is too great. It's also a metal and a non-metal. We're going to call this ionic. Okay. The mu is slightly larger. That's massive. 6.24 says that is absolutely polar. And in fact, this is to the point where it's no longer just slightly polar. We would say that the fluorine is a negatively charged and the lithium is a positive charge. Those things would be more just spheres connected to one another as opposed to actually bound together. I don't have to do a polar vector because I have a positive and a negative region. So what do we know? What we should say is if I have an increase in mu, which is the, again, dipole moment, we have a greater, it's a greater dipole, which is more polar. To the point where you turn something ionic and it's no longer polar, it's beyond polar, right? It's ionic. Okay. So in order to measure the dipole moment, it's based on, dipole moment is based on two things. It's based on that charge difference. It's based on that charge difference, Q minus Q plus and R. So if you wanted to measure it, this is actually the equation for it. I don't believe you're going to have to know anything other than, at least for the test or anything, but distance and radius. So the closer they are, the greater that dipole moment can be. Again, let's just take a look at the numbers here. If I increase Q, we see an increase in dipole moment. And weirdly enough, if we increase radius, we also see an increase in dipole moment, which is actually not true. So I think R may not be radius, but actually it is going to be radius. So yeah, that's what you should get. Increase in R, you increase the dipole moment. That's why. This has to do, the reason that this is because of polarizability. But we're going to leave it there. Polarizability is the ability to shift electrons, and it turns out that that can be a thing. So yeah. So here we have HF, HCl, HBr, HI. Okay, just in terms of charge differences, you can definitely see the dipole change, right? So there's a greater partial negative here, and in fact, we can do this kind of. So if this is HF, we would say something like this would be a lot smaller. Okay, all right, good. Again, dipole to electric. So we use both of those things to indicate polarity. It's important. Do you recognize that? All right. indicate the polarity on each of the following bonds. So go ahead and indicate the polarity on each of these. And in fact, I'll draw them for you because we'll do Lewis structures later. You should be able to do these Lewis structures, so I encourage you to do them before you take a look, but I don't have to draw all the electrons in, and we're going to use these later. So it's really important you know how to do Lewis structures, especially when it comes to molecular shapes. Which bond is more polar, which one has a greater partial negative, and we'll leave it at that. All right.